So today I will talk about general relativity this afternoon. So as I mentioned in the morning, general relativity is a subject that starts in early 20th century and has begun a big motivation for mathematicians and physicists to work together. And so as I mentioned, this is exactly about 100 years ago, and this has changed the whole question of space-time, the understanding of it. So as I mentioned, the reason that was formed was because Einstein wanted to understand how to establish a link between special relativity and gravity in order to overcome the inconsistency of action at a distance by Newtonian gravity and also special relativity, where information cannot travel faster than light. So this is a very important puzzle that has to be resolved, and Einstein looked at it. And then, as I said in the morning, Einstein learned from his teacher Minkowski about the geometry of space-time should be described by a tensor instead of a scalar function. And this is a very important realization because scalar function is simply not enough to describe gravity. And after you know it should be a tensor, you have to understand what to do, because you have to understand how to understand the Newtonian mechanics approximate the Einstein equation, which is a tensor now. So finally, Grossman and Hilbert and Einstein together wrote down this equation. And at the beginning, Grossman and Einstein wrote down this equation without this term. Without this term, the equation is not consistent. Why is it not consistent? Because the T mu nu, which is the matter density, the tensor for matter, has to satisfy conservation law. Namely, the divergence of T mu nu has to be equal to 0. That's conservation law, according to Noether. But on the other hand, without this term, the left-hand side does not satisfy that. R mu nu does not satisfy conservation law. Only after you put in this term, it satisfies conservation law. That's the Bianchi identity. So that's very important. There's a Bianchi identity. At that point, apparently neither Einstein nor Grossman nor even Hilbert knows the Bianchi identity. And Hilbert found the Hilbert action and deriving this thing naturally. So he does not know the Bianchi identity at the time. But anyway, this equation was finally written down. And this is a beautiful equation. The left-hand side is really very beautiful. And actually, Einstein said that this left-hand side is made of gold. And the right-hand side, he said he's not sure. So anyway, so this equates beautifully. This statement actually is very similar to the time when Maxwell derived the Maxwell equation. There are 4 equations that, in the Maxwell equation. 3 of them was actually derived by Riemann. The one on dB over dt apparently was not consistent when it was written. And so the missing term is exactly the conservation law again. And so finally it was written down correctly, and this is the conservation law. Okay, so Hilbert wrote down the action principle, and the action is given by the total scalar curvature of metric tensor, which is considered to be the gravitational potential. So metric tensor is a gravitational potential. If gravity is coupled with other matter, we simply add the matter Lagrangian, and then you can write down this equation. For example, you take about Maxwell equation, and the Maxwell equation has an action. You add the action with the gravity, so that you derive this equation. And now, let's come to a little bit more technical part now. So the Einstein's action is actually very important, more as important as the equation itself. Because later on, when we quantize gravity and all that, we have to look at the action. Here we look at the action again. So given a closed surface S, so I want to associate a a definition of energy to a surface. So given a closed surface, space-like, so enclose a space-like region. So a surface encloses a region, and I want to know what kind of energy you can associate to this region, space region. And this is the important question we want to understand. So we take the Lagrangian formulation, we have the actions of the Lagrangian formulation, and give definition of a surface Hamilton. So from that, we take the due momentum and all that, we can derive a surface momentum Hamilton, and turns out to be this form. And what is this form? This looks complicated, but let me explain to you. N is the normal vector, is a so-called lapse function. So given a time-like vector field, time, is a vector field, we measure time, and you decompose along the surface into two parts. One is a normal part, one is a tangential part. So N is called the lapse function because this one is a normal of the function. In space-time, you have a normal, and you multiply it by scalar, and this is a tangential part. So this gives rise to a gauge, actually, namely N and N mu. N is here, N mu is here. So depending on the time differentiation, time-like vector field, you get 4 functions. One is N, which is the lapse function, and N mu is a tangential part, and it's all here. Now, what is K? K is the mean curvature of S with respect to the space-like normal for S. Okay, so surface sitting in a 3-dimensional manifold has a normal. Okay, and this is a one is a time-like normal, and this lapse function and all that. Now, R mu is a space-like unit normal, or function of N mu along S. Okay, along S. And P is a second fundamental form of D. Okay, second fundamental of this domain D, the 3-dimensional domain has a normal because it's a hybrid surface, so it has a second fundamental form. So P is the second fundamental form. All right. So this is the setting we see. So let me repeat again. By using the Lagrangian formulation, we can derive a surface Hamilton to be this form. Now, actually, in that formulation, there's another term in the buck, so in the interior, in the domain D. But on the other hand, that term disappears in case it's satisfies Einstein equation. So when a space-time satisfies Einstein equation, the surface Hamiltonian becomes this fellow. So it is the energy according to the time-like vector field. So now, why we care about it? Because in general relativity, we do not know a special choice of time. There's no special canonical choice of time. So this becomes an ambiguity. Ambiguity comes from choice of gauge. So this quantity is a gauge-dependent quantity. After you know what the time-like vector field is, then you can derive this quantity. But the choice of time-like vector field is a choice of gauge. Okay? So that's very important. So based on the Lagrangian formulation, we can derive a surface Hamilton, which supposed to be energy, and it has this funny form. It's actually not that funny in a way. K is the mean curvature, which we like to use, and P mu nu is the second fundamental form of the 3-dimensional manifold it bounds. So, but anyway, this is derived in a physical manner and very nice formulation. The problem is how to handle this term. So the geometric quantities, therefore, are determined by several things. By space-like region where the 2-dimensional surface bounds, and the gauge choice of time-like vector field along D. Okay? So given the surface S, I bound a space-like region D, and I make use of the space-like region D and the gauge choice of time-like vector field along D, namely W mu, I've produced this quantity. Okay? So P mu nu is the second fundamental form of this D, and K is the mean curvature of the 2-dimensional surface with respect to R mu. Now, what do you do with that quantity? Well, in the whole problem similar to Yang-Mills gauge theory, a very important question in general relativity is the choice of gauge. How do we handle the gauge choice? Because there's no canonical choice of W and no canonical choice of D. It's just a reference. So basically, you use a frame to measure what you're supposed to see. And there's a measurement depending on the choice of D, and the measurement depends on the choice of W mu. And so what do you do? Okay, so that's a major problem we have to overcome. And this formula actually was known to many people since 1960s, and was used by Brown-York and Horowitz and Hawking. Now, first of all, we know that Einstein calculated perihelium or mercury and the light bending predicted by the Schwarzschild source of the Einstein equation, which was found shortly after the equation was found. This was a great triumph for the Einstein equation, Einstein theory of general relativity. However, the whole theory is highly nonlinear, and the geometry of space-time is dynamical. So the actual understanding of Einstein equation actually was very difficult, even to Einstein himself, because you want to interpret the classical Newtonian mechanical questions in terms of Einstein equation. What do you do? The equation is very nonlinear. So first of all, there's something which is unusual beyond Newtonian mechanics. Namely, there's radiation. Gravity has radiation. And this radiation was predicted by Einstein coming from perturbation of space-time itself. Now, in Newtonian mechanics, space-time is static, so there's not much radiation you can talk about. Here, but the gravity itself, space-time is moving. So you get radiation. And this was, as I said this morning, was discovered recently. And in fact, Einstein proposed this concept, and later, after 10 years, he retracted this idea. He, in fact, wanted to publish it, and then the editor stopped him to publish it. So in a way, good luck, so nobody knows that he retracted this idea. And then it was found to be okay. Now, the second thing is that it's interesting. Einstein thought that the equation itself determined gravity completely. Because he thought, now I found the equation, so everything is fine. But it's not fine, because when you have an equation, you have several questions you have to deal with. One is boundary condition, one is the initial condition. Einstein's equation is a hyperbolic equation, so there's a question of initial condition. And the initial condition has been bothering people for the last 100 years almost, because what is the initial condition for gravity? And this especially for the cosmology question, and Hawking has been asking that for many times about what the initial condition should be. And so Hawking has proposed several interesting ideas to overcome that. So we cannot tell exactly what's the initial condition for the field equation. And we also have difficulty finding the boundary condition, the right boundary condition. We now use a lot of idea assuming it's asymptotically trivial. In the case of asymptotic trivial, this means that we are looking at an isolated physical system, far, far away. We are watching at a galaxy far, far away. And therefore, it should be near infinity is trivial. That's the most natural case that we know how to find a boundary condition. But on the other hand, if we are dealing with a body sitting in a black hole, near the black hole and all that, we cannot quite set it to be that. And actually, the problem of boundary condition is one of the most tough problems in observation because it still depends on numerical calculation for gravity. And the numerical calculation encounter problem boundary condition. Because you cannot calculate an infinite domain, you have to set up some boundary condition to make it work. So if the boundary condition is not set right, you will get a wrong calculation, wrong answer. So that's a problem. And there are many problems in GR which is not solved. Many of them need deep understanding of geometry analysis. So the first question is the nature of singularities. And black hole appear in Schwarzschild and chaos oceans as an important question in understanding singularities. Why is it important? It was believed to be a generic singularity. So in fact, Penrose proposed a famous question of cosmic censorship. And basically, in a very vague manner, it says that a generic spacetime, what does generic mean? It depends on initial data. One condition one explanation of genetic means among the space of initial data, you choose some open dense set as the initial data. So in that space-time, every singularity should be hidden behind some membrane similar to black hole appear in the Kerr or the Schwarzschild solution. So that was one of the proposals made by panels. And this is very important. It's called cosmic censorship. Why is it called cosmic censorship? Because if this cosmic censorship is wrong, then you can see the singularity from far away, and it's called negative singularity in that case. This will cause problem. That means the prediction of the universe would not be predictable based on the initial data that we know of. And this will be philosophically very different from Newtonian mechanics, Newtonian physics, where we assume everything can be predicted in the future based on what we know now. So this could be true, but there's a question whether it's true or not. And this is a mathematical question, a very difficult mathematical question, still far away from being understood. So the dynamical problem is not solved, and it's only understood in a very weak field limit case. For example, crystalloidal Kalman assume the things are very small perturbation of the Minkowski space-time, then you want to understand it. In that case, you can have a reasonable good understanding of that. The reason being that in that case, there's no singularity at all, and that's good. Now, well, in order to make progress on this difficult question in general relativity, on cosmic censorship, or the structure of the universe, it's important to understand the physical quantities that appears in the equation that you can derive from the equation. And that's what we are trying to address too. Now, in hyperbolic equations, one of the very important methods to understand hyperbolic equation was something called energy method. So what do? You start out from the initial data, you have some total energy, and energy are good or positive, and then you look at the evolution of the wave equation, and the energy is preserved. So therefore, no matter what happens, the energy governs what's going on, and use that energy to control the local behavior of what's going on. So you can use Sobolev inequality, you can all kinds of inequality to control the local data. Now, unfortunately, in the case of general relativity, we don't have that kind of energy to spare with, to understand. The total energy was defined in the case of asymptotic flat spacetime, and that one is conserved, the ADM mass, but that ADM mass is difficult to use. It's very nonlinear. And also there's something called bounding mass. Bounding mass is also quite good. It decreases, and that's very useful also because those radiation come out from the energy declining and radiate out. But also that one is also very difficult to use for purpose of mathematics. So therefore, it's a strong motivation to understand what's going on for quasi-local situation. So given a region to you, can you assign some kind of energy so that we can use something similar to energy method to understand what's going on. Okay, now all this problem has something to do with choice of gauge, as I've just mentioned in the second page when I wrote down the thing. And this was a big problem for a long time. Einstein succeeded, as I said, to define the total mass for isolated physical system, which was made precise by the famous work of ADM. And it was an important quantity to measure the whole physical system, the whole one. But to measure the detail of the physical system, we cannot use it only because it's a total mass. And so we have to understand what to do and how to find a gauge-independent physical quantity that can measure local properties. Local properties are important, as I just mentioned to you, because we want to understand the detail of space-time. And as I explained yesterday, it's almost it's impossible to find mass density of gravity in general relativity, because the gravity in general relativity is nonlinear phenomena. It's not just matter only; it's the gravity interact with itself because it's nonlinear. And being nonlinear, it's impossible to find mass density because the mass density would have to be the first differentiation of the metric tensor but it can be set with 0 in a suitable chosen coordinate at any point. And so the first derivative could be chosen to be equal to 0 at one point. And the equivalence principle says that what you get should be independent of choice of coordinate. And therefore, the mass density, if it exists at all, has to be 0. And so therefore, this is not good. And yet we know the total mass in a space-time is not trivial. So this cannot be true. There's no mass density. So we still decide to measure total mass in a space-like region bounded by closed surface. So this is what we want to do. And the mass due to gravity should be computed from the intrinsic and the extrinsic geometry of the surface alone. That's what its local means. So given a surface, we want to compute some energy controlled by this surface in the region. And it should be independent region inside. In a way, this means conservation law. Because given a surface, you measure the energy within here, within this domain. You may have different way to bound this surface, and you will get the same quantity as long as the first fundamental form and the second fundamental form are given. Then whatever surface you get the same answer. Okay, so this is what part of the conservation law. Independent choice of D, of the region that I was mentioning before. So this is a rather important question. In fact, in 1979, when I have a seminar, well, more than seminar, constant lectures, and panels gave 3 lectures in Princeton on GR, on general relativity. And the first important question he want to ask is the quasi-local mass. How to define such a mass that we can compute from the intrinsic and the extrinsic geometry of the surface alone, and not including the region that it bounds. So that was a question. So independent of the region it bounds means it's conserved quantity. But this has been going on for a long, long time, including Penrose himself, Hawking, Horowitz, Brown-York, and many others work on this problem. And many definitions were given. In fact, Penrose gave definition which is a complex quantity, and Hawking gave different quantity which are useful, but they are not positive, and it's not quite right. And so is all these people. So it took a long time for me to understand this problem. It took 30 years, actually. And as a mathematician, I try to understand what do we want from a quasi-local mass. And you want to define a concept, and you have to understand what you want. I mean, it has to relate to what physics tell you. And the best that we can come from physics is this quantity that I mentioned to you. This quantity is derived by Hamiltonian formulation of GR. So this is a good quantity. So it's good. But unfortunately, it depends on the choice of gauge, the timeline vector field, and also the D. Okay? So the choice of gauge there. So to derive up to here is a very reasonable method based on Hamiltonian mechanics in classical mechanical theory. But now we have to deal with how to choose this W nu and also D. Okay? We don't want to depend on it. So I put down some definition that you should satisfy. First of all, it should depend only, as I said, on the first fundamental form of the two-dimensional surface and also the second fundamental form of the two-dimensional surface only. So that's the first thing. Second thing, it should be non-negative and 0 for any closed surface sitting in a trivial Minkowski space-time. Okay? Such a surface would produce no energy when you are sitting in a trivial space-time. You are not supposed to measure anything because you're sitting there. Now, this fact is actually a non-trivial fact. It should be non-zero. Well, of course, you can, for this statement, you can make it to be identical 0. But what you said is that it should be strictly positive if it cannot be embedded into space-time, trivial space-time. And it should converge to the familiar ADM mass, which I mentioned earlier. For asymptotic flat space-time, if we have a sequence of coordinate sphere on the three-dimensional slice that approaches the spatial infinity of an asymptotic flat slice. So we have to recover something that is well known and that is well understood. We better recover that. So the second definition is make sure we recover the existing definition for asymptotic flat case. The third one is convergent to Bondi mass when the sphere divergent to the cut at now infinity. So this is the Bondi mass, is a mass that measures radiation. After radiation radius, where you still have the mass. There's something called Bondi mass loss formula. And all these are very important concepts developed in the last 40 years on TR. ADM mass and Bondi mass are good definition, and we better recover it. So that we need that. And then it should be equivalent to standard Coulomb mass in a stationary space-time. And this was the concept when you have a sphere, SU2 action on a space-time. You want to define a mass which is called Coulomb mass according to the procedure of Eminota. So use that. You want to you can define mass, and we want this mass that we are talking to recover this mass. Okay, so that's the fourth concept, and this just based on that is not so easy to produce, and this is rather interesting. In the case of time symmetric case, that means I assume the second fundamental form is 0. And my former student, Robert Barnett, actually proposed a definition which set the order about properties. But his definition first of all, has assumed time symmetric case. Second of all, does not allow him to give an effective calculation of the mass. He defined it by process of minimizing. So it's not good enough. And about 15 years ago, I was interested in how to formulate criteria that exist in a black hole. That keep on called Hopf conjecture, actually. And this statement says that if the way that I formulate it is a quasi-local mass of a closed surface is greater than certain multiple of the diameter of the surface, then the closed surface will collapse to a black hole. So this is basically a interesting statement that you can state it in a layman terminology, and yet it's very good geometric quantity. But here, of course, we have to define what is quasi-local mass. Otherwise, it doesn't make sense. So for this closed surface, if the mass is reasonably big, how big? Greater than the multiple of the diameter of the surface itself. Or sometimes people use the length of shortest closed geodesic in this surface. But this is not really too important. The important thing is that if the mass is large compared to some length, some scale on the surface, you want to say that you collapse to a black hole. So in this formulation of the Hopf conjecture, one needs a good definition of what is a quasi-local mass. So in order to do it, we have to work hard on understand what is going on. And actually, I did something with Rick Shern on this problem about 30 years ago when I was in Princeton, and that was quite good, but it's not satisfactory enough. And I in about 15 years ago, based on some work that I did with Witten, I understand the boundary effect of the mean curvature for the existence of black hole. So I did this in about 1999. The boundary mean curvature actually contribute to the black hole existence. So I suggest Tam in Hong Kong to look at this recent work that I did. And I mentioned that the work of Robert Barnett on something called quasi-local spherical foliation are useful. And Barnett did a remarkable calculation turning part of prescribing scalar curvature into a parabolic equation. So he was able to understand how to parameterize a space of manifolds with positive scalar curvature using a parabolic equation. And that was very nice work. And then afterwards, Tam told me that he generalized the statement with Tam to the case when the manifold has a boundary which is round. And this was very nice. So then Melissa Liu and I start to generalize this statement, C and Tam, to the case when it is not time symmetric case. So C and Tam study the case when it's time symmetric. And this becomes a rather interesting statement because this is the first time we were able to understand how to prove some positivity of quasi-local quantity. So the total mean curvature is replaced by the total integral of the space-time length of the mean curvature vector in the work that Melissa Liu and I did. This quantity is independent choice of the free manifold that the surface is bound. So what we do is that we isometrically embed the surface into Minkowski, into Euclidean space, and we take the difference. And we define that this to be quasi-local mass at that time. That was about 12 years ago when Melissa Liu and I did this thing. So we define the concept of quasi-local mass, Melissa Liu and I, that to be the integral of the length of the mean curvature vector. And we isometrically embed into Euclidean space and also in the space-time and take its difference. And we define it to be the quasi-local mass. This was quite good because we can prove that it's always positive, and the proof is not trivial at all. And then, but there's a problem. First of all, before I demonstrate there's a problem, there's a work by Brown and York and Hawk and Horowitz, which I did not know at the time when I worked on it. They actually has also studied the problem in the time symmetric case, and different from what Melissa Liu and I did. It's more gauge-dependent quantity, but they are not positive. Only the definition Liu and myself turns out to be good and satisfy most of the properties that I mentioned above, the 4 properties I mentioned. But unfortunately, the Liu-Yau mass is not positive, it's too positive. Why is non-negative is too positive? What does that mean it's too positive? It may not be trivial for surfaces sitting in the Minkowski space-time. So even the surface is supposed to create no energy, it creates energy. So that's too positive. So this becomes a problem, and we need to correct that because it set up most of the properties except the first one. So only about 7 or 8 years ago, Muda Wang in Columbia and I changed the definition and becomes good now. So we consider the embedding of the 2-dimensional surface into Minkowski space-time instead of embedding into Euclidean space-time space. And this embedding is no more unique, and we have to optimize the quantity among all isometric embeddings. So this is an interesting geometric question that we have to deal with. So let me explain the definition now. So given a surface S, we isometric in that surface into the Minkowski space-time. This can always be done in the case the surface is diffeomorphic to S2. According to a theorem of Pogorelov, you can always isometrically embed a surface into hyperbolic space form of suitable negative curvature. And then the hyperbolic space form can always be isometric embedded into Minkowski space-time. Therefore, any surface can be isometric embedded into R3,1, assuming the topology is right, namely genus equals 0. And then after embed, this is the reference space-time now. So what we are trying to do is that a surface is inside a space-time, and then I want to move it to the trivial Minkowski space-time, and I want to compare them. So the situation in R3,1 is like the observer. It's a frame to observe the space-time. Okay? So that's the way that we look at it. So a surface is sitting in Minkowski in a physical space-time, and I use Minkowski space-time to observe this quantity. So I isometrically embed the surface into R3,1 and try to observe what's going on in the physical space-time. So what I do, I take an observer in R3,1. So in the Minkowski space-time, there's an observer, and he's traveling along the trajectory given by timeline vector W. Okay, so timeline vector is a vector, and of course a vector defines some trajectory, namely straight lines, and then the observer is standing in the Minkowski space-time. He wants to look at what's going on this surface after you isometric embed. Okay, so when you do that, you find out a quantity. It's H0 dot with W. So what's H0 W? When the observer is watching on this quantity. You see, this is sitting in Minkowski system. This is surface, and this observer going on, and she observed this surface at this point. Let's say H naught dot W is what? Is the expansion of the contraction of the surface area at this point along the observer W. So you remember, I'm taking mean curvature vector dot with a vector, normal dot with a vector, a constant vector. This corresponding to the contraction or expansion of the light bombard at the surface. You know, the surface. The light bombard on the surface and it bounces back and it can contract or expand depending on the curvature of the surface. And this is the mean curvature vector, mean curvature in the direction of W. So left-hand side is a very physical, interesting quantity, namely whether light will bend or will contract or expand. This is an important quantity that has been used extensively by Hawking and Penrose in proving the singularity theorems that they proposed. And so we felt this important. The H naught dot W is the expansor. Now what do? We come back to our physical space-time, which we have no choice of gauge. So we said, okay, we set it, the expansion or the contraction, to be the same. Namely, at this point, I define W bar. W is here, is defined already. It's a trajectory of the observer. But on the right-hand side, on the physical space-time, I define vector field along the surface by equating them to be the same. So along the physical space-time, I want a vector field which satisfies this equation. And this W bar is uniquely determined at each point on the surface. Okay? So this is good. And in this way, W nu can be written in this form, and W bar can be written in this form. So what I have achieved is that I have now give a good definition of the gauge, N and N nu. Namely, I have defined what my timeline vector field W bar is. So let me repeat again. One of the major ambiguity I encountered was the choice of this W bar before. So let me show it back to you. At the very beginning, we have this. See, we have the choice. We have the choice of this property, N and N mu, and namely choice of W mu. Now I give a choice. The choice was coming from the observer in the Minkowski space-time. So you see, using an observer moving in this direction, I define this mean curvature the observer sees on the surface, and I divide W bar so that they give the same expansion or contraction on this part. So W bar becomes a vector field, timeline vector field along the surface. And once I have W bar, I have the concept N and N nu that I need to define in the previous thing. So this gives me a good way to understand the definition of W bar. Okay? And this is good because now, given the surface, I can isometrically embed into alpha 1, which can always be done, and then I divide W bar. But there's a problem, namely there are too many isometric embedding into alpha 1. If you embed into Euclidean free space, it's rather unique, but embedding into Minkowski space-time is not unique. So you have to change something. But in any case, we have this concept. Now sitting in alpha 1, you have the K naught, which is the mean curvature vector, and the P naught that we defined earlier. And so this is good. And a very important observation that we make was that this total quantity is actually a very interesting quantity. Namely, it's rather complicated because of P naught there. But what we do is that we project S onto the orthogonal complement of W mu. So you see, I can project alpha 1 along W mu onto the hypersurface. I take a hyperplane, which is orthogonal to W mu, and the whole surface will project down to a three-dimensional alpha. So the surface will be sitting in a three-dimensional alpha. And turns out this quantity, which is complicated, becomes the mean curvature, total mean curvature of the image of S hat sitting in the three-dimensional space. So although it looks complicated, it becomes a simple conclusion. Is the mean curvature of project surface into R3. And this is very good because now we have a good interpretation. So everything is nice now because we understand it better. And so is this picture. You project the surface in the orthogonal complement of W nu, and you get this S hat. And that quantity we are looking at is actually just the mean curvature of S hat sitting in R3. So it's very natural. Now, we define a similar quantity in the space-time because in the original space-time, I have n, W hat, I have the n, and then I define this concept, which was the original definition in space-time. So this part in the space-time. So we define EW to be this quantity minus the quantity that we found in Minkowski space-time, the difference of them. So we look at this quantity which was found by Hamiltonian mechanics and subtract out the one that you found in Minkowski space-time in the reference frame. And this difference turns out to be positive, which we prove. And this is a non-trivial proof that we actually know this difference is positive. Okay, that's the first important achievement is to prove the positivity of this difference. And as I mentioned to you, n and m was chosen according to the reference frame, the observer, and with minimizing among all possible isometric embedding into R3 and the timeline unit constant vector W. So that's what we do. And in this way, I have found a mass according to this minimum. Okay, and this is turns out to be very important. And the fact that you have an infimum because this guy is positive, non-negative. So non-negative quantity always has a minimum. So that's good. And now you have to look at the all possible isometric embeddings, and you look at the one that optimize the energy that I just mentioned, namely minimizing energy. And we calculate the Euler-Lagrange equation for such a thing. We know how to deform the isometric embedding, and we found an equation. The equation may look complicated. It's actually not so bad. Tau is actually the height function. If we project the surface in the three-dimensional linear space at the height function, and we call it timeline function, tau, and you calculate this quantity on the two-dimensional surface, and you define sin theta to be this, and then you get this equation where mean h is a mean curvature, and you can define a condensed one form, and all this can be calculated completely from the surface and the second fundamental form and the first fundamental form on the two-dimensional surface. So this is a fourth-order equation. Fourth order because theta involves a second order already, and then you differentiate again, you get fourth-order equation. Okay? Now this fourth-order equation is actually an elliptic equation. So it's a nonlinear elliptic equation, and you can prove existence and all that without much problem. And you may have isolated singularity and all that, but it doesn't bother us to use this one. Now, it's very interesting to know what to do with this equation. And we know that EW, as a result, is non-negative. And we call it admissible isometric embedding when you get the embedding like that, optimal embedding. And this, a very interesting question is, under what condition is you need this solution of that? And we can compute this one in many important cases explicitly, actually, perturbatively. All we need is perturbation solution, but we know it exists. So that's not bad. And so now we have defined our energy because I take the minimum, and that's our energy. Okay. Now I choose a translator vector. I define a concept of energy, and this energy depends only on the choice of the surface, second fundamental form, and the first fundamental form. And in fact, you can associate a 4 vector to it. And this one will be the linear momentum and energy momentum vector. And this guy satisfies the concept of Lorentzian invariant in the reference frame because in Minkowski space-time, there's Lorentzian symmetry, and it's invariant under that. And it's trivial for surface sitting in Minkowski spacetime, and future timeline for surface in spacetime, which satisfy the local energy condition. So that's part of our proof of the positive mass conjecture in this form. And then we also prove, this is actually non-trivial, to prove that on the space-time hypersurface, it will be convergent to the well-understood ADM mass. Now, if the ADM mass is defined in the asymptotic flat way, which is asymptotic in a very strong sense, the proof is not hard. But it may happen that asymptotic is not strong enough. This is what is called boost situation. Boost, and that case takes more work, and that's non-trivial work. And in the case of limit along a null cone, we obtain the bounding mass. And so all this are true, and when we take a limit along a point along a null geodesic, we can recover the energy momentum tensor of matter density when matter is present. So given a point in space-time, we look at the light cone at that point. And then we take a small sphere accordingly and then converge down to a point. We can take a limit and we found the energy momentum tensor of the matter density if the matter is there. So this quantity will recover the matter density if matter is there. But if matter is trivial, that means there's no matter, we recover something called Bell-Robertson tensor in vacuum. So this recover the curvature tensor of space-time. Part of space-time is called Bell-Robertson tensor. This Bell-Robertson tensor was actually used pretty extensively by Quasilocal and Kleiman in their work. So in this limit, first of all, the fact that in the limit it exists is already non-trivial because it says that the energy is finite. You remember in quantum mechanics, in quantum field theory, we always have to avoid the self-interaction energy. Here it says that it's finite. And this problem, properties of quasi-local mass is likely, as I mentioned yesterday, to characterize the definition of quasi-local mass because I think it's very difficult to achieve such properties with all these properties. So I think it has to be equivalent to each other if it really exists at all. And we proved that it exists already. So what I'm asking is whether it's unique in a suitable sense. Then that means any mass satisfying these kind of properties should be the same as this one, up to an equivalence relation. Now, actually, I cheat a little bit. When I say associated closed surface, a 4-vector is not quite a 4-vector. It's actually a function defined as light cone of the Minkowski space-time. Because given a vector on the light cone, I associate observer, and I do all the procedure, I get the function. If this function turns out to be linear, then the function can be defined as a 4-vector. But in general, it's not a 4-vector. It's a nonlinear function. Now, this is actually reasonable. Why? The function is actually becomes linear if the surface close to be a sphere at infinity, spatial infinity. This function becomes linear. And the 4-vector is defined, and the ADM 4-vector is exactly this vector. Why is it reasonable? Because things become linear only when the field, gravitational field is weak. You don't expect it when the things are interact in a strong way that the answer would be linear. And so, so the nonlinearity of this function is actually should be used to detect the strong field of gravity. And this is not studied well, and so far we don't really know yet how it goes. And this is same when the sequence sphere convergent to now infinity in boundary coordinate. Then in there, we expect it to be also a 4-vector, the boundary sucks 4-vector, which turns out can be proved. So these statements can be proved. So as I said, this function is actually nonlinear. And in general, the Euler-Lagrange equation is not trivial to solve. But in the case of the nonlinearity, it turns out, as I said, is solvable. It's more linear if the mean curvature starts to be convergent to some nice round sphere, like here. And we can, based on this, we can actually solve the optimal embedding problem asymptotically. So we can solve it when the surface is going to infinity in a suitable sense. And so with that assumption, we can actually find the quasi-local mass can be defined this way. This is actually a very nice quantity, although you have to look at it for a long time to understand it's nice. This form is actually not too bad if you think about it carefully. And this relates to this vector, that time function we call. And now, the ADM mass and the linear momentum are actually turns out to be this term. So if you compare the previous definition, then we get the definition here. And in the case of Yau cone, we study it with chain, Punnan chain together. And this is the limit of quasi-local mass of this form. These are related to the Bondi-Sachs energy momentum. So this comes out to be right. So this is a finite quantity that we have, and this finite quantity we have only when R goes to infinity. It gives rise to the right quantity. And this, all these are invariant under Lorentzian transformation and all that. Now, the 4 vector is equivariant with respect to Lorentzian transformation acting on the surface at infinity. And this is important. So why is it important? Because we want to boost the isometric embedding according to energy momentum at infinity. This allows you to give all kinds of important properties of quasi-local mass. So this is to give a more precise statement of what I said. When you are taking a point, you take the cone, future light cone at that point, and you look at the 5 parameter along this CP, and you can define the sphere to be level set of the 5 parameter. So you take light cone, you cut it, and you get a SR. And you want to evaluate of this mass of this light cone and see what happens. Well, we calculate, and then we found this following contribution. This is the metatensor. So in the R cube term, you get a metatensor. Now, R cube is right because the sphere has R cube. And the quantity of the ball is this. So divide by this ball, you get this tensor. You get the metatensor. This is exactly what you expect. Divide out by the ball, you get a metatensor in R cube. That's assuming the metatensor is non-trivial. But then, when the metatensor is trivial, the limit will appear in the 5th term. And this is the Bell-Robinson tensor, depending on the curvature, quadratic in the Y curvature tensor. So this comes out to be good also. So the Y tensor will appear. And this is the same as what Hawking did, and was computed by Horowitz and Schmidt. So this quantity is also very consistent, much consistent of the known quantity that was done by other people before. So then now the question is, so we can define a quasi-local mass. We want to define something more general, not just the mass, but also the concept of linear momentum and concept of angular momentum and center mass. All this has to be defined. These are all classical quantities that appears in Newtonian mechanics. We need to deal with them. Well, this is natural. Because in the previous case, we use a vector field, which is constant, a linear translation. And that's how you're supposed to get mass, or mass linear momentum. But use rotation and all that, then you get angular momentum. Okay? Boost Killing field give you the center of mass. So let's take a look. First of all, we rewrite the equation that we had written before. This is very important, the rewriting. We define this low to be this quantity, where x0 are the mean curvature vector in Minkowski spacetime, and h is the mean curvature of the physical spacetime. And tau is a time function satisfied by the fourth order equation. I call it low. Okay? This is a density. We call it quasi-local energy density. So it's different from the Newtonian density. And then I divide J to be this quantity, which we call momentum density. So this is an observation that we found by looking at the equation carefully. Then we found, in that case, the isometric embedding problem has this simple form. It's divergence of J equals 0. The complicated fourth order equation becomes this interesting divergence form. And the quasi-local quantity now has this very respectable way. It's very similar to what Noether did, Emmy Noether did. So we can now just take a Killing field in space in Minkowski space-time and plug that in this way. And we define E to be this. And T0 is simply a time-like vector. Time, x0 is time. A is a Lorentzian transformation. So you can achieve any Lorentz transformation by using this. And you define this concept of E. This is called quasi-local quantity. So now you can use many different ways to plug this quantity in and get different quantity. One vector field corresponding to this formulation is this rotation vector field. So A acting on rotation vector field, or A acting on this boost vector field. This one will give you the angular momentum, and this one will give you the center mass. So besides energy and linear momentum, you can define quasi-local mass, or quasi-local angular momentum, or center mass, and by plugging in this formula. Well, these are rather remarkable thing. It's set the same property that we had before. Namely, they are trivial if the surface is sitting in Minkowski spacetime, which is what you expect. But also, they satisfy some classical transformation law under the action of the Poincare group. So what is the quantity? Well, I can define the angular momentum and the center of mass. Then they satisfy the following important property. That means the total angular momentum and total center mass are finite on any vacuum asymptotic flat initial data set order 1. Now, this is a rather interesting fact because the total angular momentum was considered by many people in the subject for a long time. But they are not always finite. And we finally understand it through the quasi-local formulation. And also we prove this rather interesting statement. You differentiate the center of mass with respect to time according to Einstein equation, the Einstein evolution equation, then is equal to pi divided by p0. So this is what you expect in the classical Newtonian mechanics. The motion of the center of mass multiplied with the mass becomes the linear momentum. And this was unexpected to us at the beginning because this calculation is very non-trivial calculation. This involves the dynamics of the Einstein equation now. as I mentioned to you, the definition of angular momentum has been proposed by many, many people also. And most of them does not turn out to be good because they are divergent. And in our case, it turns out to be good. And it's rather amazing, actually, because we didn't expect that you can solve it in this way. So let me explain it to you a little bit. Well, the metric tensor is supposed to be equal to the Euclidean metric up to some order. Q and P, like this. And usually we assume these two conditions. Now, ADM mass is easier to define and infinity, but angular momentum goes a little bit higher order, so that becomes non-trivial. And there are many people has approached this problem, including this set of people, and they consider asymptotic rotating Killing field. Because this expression J actually diverges. If you are not careful, this actually diverges. And therefore, you have to be very careful how to make sure that it's finite. This is very interesting because if you did wrong, you found counterexample. An interesting counterexample is that it's found by 4 of us. Even in Minkowski spacetime or Schwarzschild, you can find metric hypersurface with satisfy this condition. And yet, the ADM angular momentum is not 0. And this, of course, is wrong if you define it in the way that ADM define it. Because in Minkowski spacetime, the answer should be trivial. And yet it's not. That means the definition has some problem. And Kusel make a strong assumption and prove that it's okay, it's finite. So the question is that the ADM formulation of angular momentum is not exactly correct. You have to change it to make it correct. So, so turns out the quasilocal definition of angular momentum is good because in the right asymptotic space-time, it gives a finite and good definition. And turns out, when we take limit, the energy and the linear momentum is fine in the limit, same as the classical definition, but not the angular momentum. Okay, but we enjoy the property that is good, and and it recover the K-metric angular momentum. And it's invariant in the K space-time also. And also, in the finiteness theorem on the new total angular momentum we define, we do not assume something called parity condition, which was assumed in the classical definition of angular momentum. I think the reason that this works out nicely is because the isometric embedding actually provides the correction to cancel all these unphysical terms to make it to be good. And also it is preserved under the conserved quantity. We proved that also under the Einstein equation. So we can take a limit to large sphere, either spatial infinity or now infinity. They all come out to be quite good without assuming any more restriction on the sphere. Now, finally, I want to talk about radiation. But what time am I supposed to stop? Few o'clock? Oh, okay. Now, this is an important question for radiation. Most of the argument about radiation depends on numerical calculation, which is not clear to be valid, actually. Here, we deal with a very concrete and important case, a K-metric, or Schwarzschild metric, but allowing angular momentum. This was started by Chandrasekhar in a very complicated calculation. The whole calculation consists of a whole book of about 300 pages long. And you perturb the K-metric, you want to understand how things come out, radiation, the energy and all that. So you take a sphere and push it all the way and try to see how the geometric data behave. So let's look at this quantity. This was geometric, and we do a perturbation. Perturbation here, here. Okay. Q2, Q3 equals 0 was the original Schwarzschild metric. Well, it was proposed, and Chandrasekhar proposed and tried to understand how to do the perturbation. So he write down ansatz, and he can solve this by separation variable. Okay? He write down this, where this guy solved some equation, namely the Regge-Miller equation of this form. So sigma and mu appear here. Okay, sigma. The separation variable constant. If this quantity solve this equation. Okay. So mu and sigma are related to, one is a frequency, one is a separation variable quantity. Okay, and this all relate to here. Okay. Okay. Now, we perturb this space-time metric, which is Schwarzschild. So I take a Cartesian coordinate in Schwarzschild, given this. So D is defined by this quantity. Okay, satisfy this property. So what does that mean? So let me show you a picture. So this is Schwarzschild metric with a hole here, and this is a faraway sphere, sigma d, and I take a sphere here, okay? A sphere, small sphere, okay? So it's this sphere, sigma d, okay? Center at d. Okay, what do I do now? Well, I want to measure the gravity inside here. See how it changes when d goes to infinity. Well, you solve these two equations, turns out. And see, we need to calculate the energy. The energy is calculated by isometric embedding. And we do a linear perturbation and found this equation. And we solve it, the linearized equation. From here, we found the following thing. The quasi-local mass with the optimal isometric embedding can be written in this form. 1 over dq is the distance. Okay? So the quasi-local mass at infinity of a small ball can be calculated. And turns out to be this form. Okay? Where E1, E2 can be written in this form. This is a long calculation, but it works out nicely. And we know the answer. And turns out we can calculate quasi-local mass density as was defined earlier. It turns out it's a complicated quantity. Well, so we look at this quantity and integrate it. The first one integrated with 0 is of order 1 over d. And this is something called mass aspect of the Hawking mass. And 1 over d squared term is our quasi-local mass, etc. So we get this important quantity that we try to understand. And so each of them we can calculate using separation variable. So all this can be calculated in all this quantity. It's a very interesting fact which we found, which was not noticed before using the concept of quasi-local mass. Namely, when you perturb Schwarzschild space-time of something called purely polar type, namely you assume one of the quantity equals 0, it turns out the perturbation contradicts the positivity of quasi-local mass. This was not known before. When Chandrasekhar did his calculation, he thought every perturbation allowed. What we found is that infinitesimal calculation, infinitesimal perturbation can be obstructed. That means if you perturb in a suitable manner, it will violate the energy condition, and therefore it cannot exist. So this gives rise to a way to understand what kind of perturbation is allowed. And it also gives you a way to measure how to measure gravitational radiation using the quasi-local energy. And this presumably can be put into experiment to observe. There's something to do with the limiting sphere and now infinity, how the gravity behaves. So it could be used to detect the gravitational wave, and hopefully can use, based on this, to detect the angular momentum and the mass of the original source if it's one single body. But we have not done the calculation for two-body calculation. Two-body calculation is complicated, and nobody knows how to do it anyway. The question is whether we can do a better job or not. We don't know yet. But at least in one-body calculation, we have getting more information than what people know. Namely, we found obstruction for some kind of perturbation are not allowed. Well, there are also situations where we can do calculation if the model space is not Minkowski. But let me not talk about this. Let me just stop here.